So I asked Nadia to give a talk today as well, because as data becomes flooding into the building, there raises this issue of what do we do with it all? And in the case of getting to things like climate data sets, we have to figure out how we're going to reduce these data sets and yet get the science out of them that they want. And Nadia's been working on developing an approach that many of you out here may find useful in reducing those data sets. And it's called space-time gridding. So I'm going to turn it over to Nadia, and I'll wave at you when you get 2 minutes. Thanks.
Thank you very much for this opportunity. Paul, Elizabeth, Brian, and myself started about 2 years ago working with data from multi-instruments as part of one of the VIIR's CIMSS teams. But we quickly ran into problems because comparing data or retrieval products from, say, a sounder and an imager brings forth complications, especially with native instrument resolution, differences in time sampling. And so there are many different approaches, as we all know, to level 3 gridding. We especially wanted to do all our analysis on a globe and repeat that often so that we can run a whole year of data on a globe and detect trends and really understand differences between different instruments or different retrieval algorithms. And so instead of developing a level 3 gridding approach for our one specific parameter, say clouds of pressure, we adopted a more generalized approach and developed instead a level 3 or a gridding framework. And this is what we refer to as the space-time gridding. And this has since helped us to collaborate more widely, not just with people within CIMSS, but also nationally and internationally. And this is here where I would like to recognize Shaima. She worked with us during her time here this past semester. And we've had many great conversations with Ralph, Andy, and Andy. And we ourselves see ourselves now as sort of the gridding sort of collaborative here at CIMSS. And together we collaborate then internationally with UMedSat and KNMI. And I will elaborate more on that a bit later. So what does it mean to aggregate data into information, or what is the objective? It's not just about finding that one single value per grid cell. That's usually what you do for visualization, fast visualization of global data sets. Or often there's subsampling for data reduction. But we also want to be able to do science in grid space and to know that our climate data sets represent real trends and not artifacts due to data subsetting. So I've said many things here, the same things in different ways. It's about doing science in a regularized data environment. It's about neutralizing instrument differences, at least statistically, so that you know you're comparing apples with apples. We're into the future, we look to making composite data products that could be interesting, or even higher level information, not just stopping at your level 2 retrieval products, but developing environmental indicators or indicators of change or whatever the application is. So in the space-time grid framework, we are especially concerned about reproducibility. 2 teams must be able to reproduce the same level 3 product, or change another one, and then they can tell me how they did it, and I can then reproduce that, so that we can test these different ways. We all know that things are very different depending on, at least at a level 3, things can be very different depending on how you sample and how you grid. So if we can all reproduce each other's results, we can really start to do more meaningful science with that. Instrument independent, we want to throw together sounders and imagers. Flexibility too. Many different teams have different ideas about what they want to have at level 3. There's not just the type of parameter, but also the statistic that you do use to represent your data at that level. So it must allow flexibility, especially the calculation of linear and non-linear statistics. And it's a space for data exploration on a global scale, and it's fast, simple processing, and also really to support research in this grid space. So these were our goals as we set out developing this framework. So traditionally, this is how we view the approach. You have your level 1 calibrated radiances that are then with your level 2 retrieval products. This pointer is coming.
Keep talking, I'll play.
All used and
I think
all
the
off.
battery's probably going to die. And then you have your level 2, but that's all instrument specific. And then we know that for some instruments, and then we know for some instruments you have your specific level 3 gridded products. We all know the Modis one, but then for other instruments you don't even have that level 3. So how do you then compare different data sets at that level? So this is what we have been working towards. You have your level 3, your level 1 from different instruments. Then you have your different retrieval algorithms at level 2. But then all of those we can then aggregate through our space-time gridding algorithm framework into the same type of grid with the same type of filtering and the same type of statistics so that we can then do more meaningful algorithm or instrument comparisons. Here is another approach to this level 1, 2, 3. Elizabeth will talk a bit later about what we developed for sounders, a single retrieval system that handles 3 different instruments. So you have your level 3 calibrated radiance from 3 different instruments, but then you retrieve, using the one algorithm, you retrieve from all 3 instruments, and then you use the one level 3 gridding to that level 3, and then you can do real instrument comparisons like that, not just algorithm comparisons. And also then, we don't have to go from 1 to 3 through 2. We can skip 2 altogether, go from level 1 to level 3, and grid radiances or brightness temperatures if we want to do geophysical comparisons with the retrieval products. So these are just different ways of viewing this. We feel that level 3, people have often got stuck too much in thinking about their parameters specifically, but if we tease out the problem, we can identify these more generalized principles that concerns level 3 aggregation. So this is our space-time gridding framework. You start off with filtering. You have your main parameter that you want to grid, but then you can filter that based on ancillary data, like sun zenith angle, or viewing angle, or cloud phase, or whatever else. And then whichever values pass through those filters, they are then binned or gridded onto the space grid. It's an equal angle grid, and we call that a geohistogram. You have your latitude, longitude, but then for each grid cell, you have those values accumulating, so you form this histogram. Then you can stop there, because here now is a data output. So you have this one single file for a whole globe of data, one day of global data. Then you can do per grid cell, you do now ordinal nominal classification. Either you do it according to height or according to surface type or whatever else, other refinements you need to do before you start calculating your statistics. And then here, the final phase is where you reduce all the values in one single grid cell to one value that is then a statistical value, but a statistic that is very relevant to what you want to study and very relevant to your parameter. So here's another representation of this. We separate this into 2 phases, the space aggregation and the time aggregation, because we feel that this is where we can free up or open up this dialogue about level 3 and allow more people to start talking about this in a more meaningful way. So the moment you have your geo histogram, this is what I explained. This is where you do your parameter filtering, so whichever passes come sit in this grid cell for that grid cell. And it's physical data reduction because you don't store your ancillary data. You use that to filter beforehand. So you only store your parameter or value. And then you can, as a user, choose the grid size. It can be any size. It doesn't have to be fixed. So this is what you have. And then in the time aggregation, this is when you reduce this histogram to one single value. But you can do, for example, minimum sample size testing. to make sure you have significant sample size. You can do declassification. You can really do data exploration once you have this grid. To understand your parameter better and to anticipate what you may need. So you can do this time gridding, iterate through it many, many times because you have this file. So it's really fast and it's very intuitive, and it allows for many people to say, no, we do it like that, and the other person says, no, we do it like that. But then you can test it almost in real time. You can play with it and just actually have some fun instead of running into a wall all the time with these things. Here, for example, is now 2 different recipes for 2 different cloud parameters, and we anticipate that if different teams can define their gridding recipes in these 4 steps, all you have to do is pass these recipes on to a different team, and they can reproduce your results because these are the steps it takes. So it becomes much more an open dialogue. People can share their ideas more better. So here we for cloud top pressure, we use solar zenith to do a day-night filtering, and also we only want near nadir observations. Then we just grid it onto 1 degree grid, and we then classify according to low, mid, and high, and then we do a monthly statistic. That is the average of the daily averages weighed by the percentage cloudiness. So there we took some time to develop that type of statistic for us. But for a cloud optical property, you may want to do it according to water ice, the phase, and then also make sure that you only filter the successful retrievals. But you can have any number of filters up here, and that's also 1 degree. And then you can classify according to land type. You want to separate ocean and land. And then a monthly, for these optical properties, you don't have to have the month average or daily averages. You can just take all the observations and average that and weigh it by the number of observations to account for the sample size differences. So you can see now how you can use this framework to map out your level 3 gridding strategy. And now I also just want to show here how we anticipate this being implemented, or already have experience with doing this. First of all, you can have many different filtering strategies that then feeds through to the gridding phase. But then once this gridding is, these space gridding data files are about 50 megabytes for 1 day of global data, and then you can store those. And then you can iterate later on as your knowledge on your parameter or your or within your science team improves. You can redo the classification, or you can redo the time gridding. So then you can iterate through those, and these steps are really fast. The space gridding takes, I will give an estimate of how long it takes to process a globe of data, but really it allows flexibility at each of these different steps, so that you can. So we all know the nearest neighbor approach, and this is really where this whole thing started for us. Here you have a nearest neighbor of, say, modus 5 kilometer. You bind that to this 1 degree grid cell, and that now represents the value for the entire grid cell. And here you have a sounder field of view, and you want to compare the two, but really you're not comparing apples with apples here. And so we thought that if you accumulate all the values for that grid cell and at least make sure you have statistical representation of that parameter in the grid cell, irrespective of the native instrument resolution, then you can at least have more confidence in your comparison. So here is just some estimate of how long it takes. A traditional nearest neighbor approach is 13 minutes. You have, for modus, say, 280 granules a day, and you end up with one array or one file that is just 180 by 360 if you have 1 degree. And the file size is around that size. So you can see, and for the rest, you can just read there. So you can see it's very doable. And this is all just, we have a PhD student at Texas A&M running this locally on her local laptop, and she achieves the same time estimates. So, but these are just the estimates for the initial space gridding. The time gridding is in minutes. It's really fast. So once you have these files and you can store them somewhere, for a month you will have 30 files because it's 1 for each day. So it's not even that many files, and then you can just iterate through different solutions for your time grid. Here we have, we're busy now with this, and we have the VIIRS, EDR, daytime, near nadir, cloud top pressure for high clouds. This is the monthly average, and this is the same filtering and the same everything for the MODIS collection 6. And this is how they differ. And this is a difference plot of the two, just to show that once you have the data in this grid, you can just do all sorts of things. And then here we have the CRIS brightness temperature averaged. It doesn't matter what geophysical parameter you want to grid, it can go through this framework. And current and work and collaborations. We've started to work quite closely with Rob Rubling and with Ralph and Andy and through the CREW initiative. And there we are all working together to evaluate different ways of filtering and gridding level 3 products, because we need to get this dialogue going. So that is already quite well established. Then we're supporting VIIRS science teams, and we anticipate this will be implemented at the PEAT. Thanks so far to all who has helped with that. And then Shaima and her PhD student Katie Pitts at Texas A&M, they're studying how differences between MODIS and VIIRS cloud retrievals affect the vertical distribution of liquid water in ice clouds. So once you have your science question like this, you can then design your level 3 gridding approach to fit that science question. And then I'm working with Helen at Stellenbosch University in South Africa, where we combine fire data from imagers and trace gas data from sounders and find geospatial correlation so that we can see, understand differences in ecosystem fires over there, because some fires burn slower than others. So that's just it for now, but we hope to collaborate more broadly within CIMSS, and hope you can find this useful. Thank you.
Questions for Nadia?
So Nadia, I like this a lot, but it has very much a satellite focus. I could suggest another collaboration, and that's to use these same kind of tools for model satellite intercomparison. And that's something that's extremely valuable. And in fact, we're part of the NASA Air Quality Applied Science team, and sorry.
A question.
No, but I'm trying. Sage. Can't think of her name. Professor
Tracy
Holloway. Thank you. So Tracy Holloway, as part of that team, has developed something called WIPS, which is the Wisconsin Remapping Tool. And the key there is to take this data, in this case NO2, so that they can provide it to air quality modelers. And it's not that the issue with the level 3 is it's not latitude, longitude. Could you do it for Lambert conformal grids? And just add that to your suite of tools in the framework, so then you can do modeling comparison.
Yeah, that's useful. Thank you.
And again, that's getting a lot of leverage right now within the applied science team of getting out to users. And it sounds like you've built something much larger scale with this activity.
Is there a satellite data set in particular that would fit with Tracy's?
So Tracy's focused on OMI and O2,
Yeah.
and she's extending it to MODIS. But again, it's putting it not on, the key is putting it on a model-centric grid that would probably fit into your framework pretty nicely. Then another thing to consider is you're looking at cases where you've got a 1-degree grid. It's start thinking regionally, not globally. You've got a 1-degree grid, so all your satellite pixels fit into that grid, but some have lots and some have few.
Yes.
Then if you think regionally, you've actually got a lot of satellite pixels that are much larger than the region you're interested in. So how do you map onto a smaller domain than you're observing?
So the assumption in this at the moment is that you will choose a grid cell that is larger than the largest of your instrument's native resolutions.
Yeah.
Yes, we haven't addressed that problem yet. So we have gone down to 0.5 and 0.25 for MODIS, but then we can't use the errors with that.
So So there is a lot of work where even if you have a big pixel, if you oversample a point function, you actually can resolve it at a higher
I've seen
resolution.
some of that.
So again, that effort is going on. You have to think about folding that into your frames.
Yes, thank you. I should also note that we can already process most instruments with this. You just plug in a read file and then it goes through it. So in that sense, it's very easy that way. Yeah. So to incorporate any new type of parameter or new type of instrument, you just have the read file and specify the parameter.
Great. Well, thanks. And clearly, you two should talk some more. Yes.